Hello again, Mr. Bailey here. Surprise, surprise, being Mr. Bailey Maths. It's the 6th lesson on Year 13 A-Level Maths Differentiation for Edexcel's Maths A-Level content. So we've just seen the product rule and then the quotient rule. Now we're going to apply these and have a look at how we can differentiate some functions which are key. In other words, tan𝑥 is one of them, sec𝑥, cot𝑥, and differentiating cosec𝑥. We'll also have a look today at something which has been taken off the A-level syllabus and shunted into further maths, which is differentiating inverse trigonometric functions. I've left this in because I think it's a lovely application of the dx over dy case of finding dy by dx. So it's worth doing. I think it's worth keeping and showing you how it's done. Before we try that though, I do have some warm-up questions. You probably could have guessed if you've seen my other videos. This time, instead of 4, I've given you 3 to try. Here they are. So the question 3 is a throwback to the binomial expansion for year 13 with non-integer powers, and question 1 and 2 are more calculus. So pause the video now and try these on your own, and when you're ready to see the solutions, press play and just double check that your solutions tally up to mine, and if not, then please do obviously make the corrections you need. So assuming you've tried these now after pausing the video, let's have a look together at question number 1. Question 1, I would strongly suggest that you read this hint. What we need to do here is to find dy by dx of this algebraic fraction. So the key here is to simplify it. So what I'd hope you'd notice is looking at the bottom, x squared minus 25. This is the difference of 2 squares. So first of all, what I'd suggest we do is we can rewrite y with the denominator being x plus 5, x minus 5 when it's factorised. And then see if the top will factorise as well. So going back to GCSE, 2 numbers that multiply to 15 and add to 8, well that could be 5 and 3. So the top will factorise into x plus 5 and x plus 3. So by doing that, you can see now quite clearly, I'm hoping, that the x plus 5 on the top and bottom can cancel. So in other words, y is just x plus 3 over x minus 5, like so. We can now apply what we learnt in 9.5, which was the quotient rule. So if we remember the quotient rule, dy by dx is VUV, with dashes at the end, over v squared. So what we need to do here is perform the quotient rule on this y of ours. So dy by dx is v, which is the denominator. So we've got x minus 5 multiplied by u dashed for the derivative of the numerator. The derivative of x plus 3 is just 1. Then minus u, which is the numerator, x plus 3, multiplied by v dashed, and again the derivative of x minus 5 is also just 1. And that's all going to be divided by v squared, which will be x minus 5 all squared. So the top, x times 1 is obviously x. Wrong colour line. Doesn't know that it really matters, but you know, I like a black fraction line. So we have x minus 5 minus x minus 3, and that's all over x minus 5 squared. So obviously the x and the minus x will cancel. Minus 5 minus 3 is minus 8. So our solution is minus 8 all over x minus 5 squared. That's the solution to warm-up question 1, minus 8 over x minus 5 squared. The denominator can be left factorised. Question 2, given that y is cos squared x, find dy by dx. This here is going to be an application of a chain rule. So what I'd suggest we do is we let our u function to be cos𝑥. So in other words, we have y equals u squared. If u were cos𝑥, then du by dx, differentiate cos𝑥 with respect to x, gives us minus sin𝑥. So using the chain rule, dy by dx will be dy by du times du by dx. Now if we differentiate u squared with respect to u, that will give us 2u, and du by dx is minus sin𝑥. So Replacing u with what it was in terms of x, u is cos𝑥. So using that here, we've got minus 2 times u, which is cos𝑥, multiplied by sin𝑥. So we have minus 2 sin𝑥 cos𝑥, or 2 cos𝑥 sin𝑥 if you wrote it in this order. Question 3. F of x is the root of 9 minus x, where the modulus, the size of the variable x, needs to be less than 9. Find the binomial expansion of f of x in ascending powers of x up to and including the x cubed term. What I'm going to suggest we do is to rewrite this as a power in index form. So square root means power half, so this gives us 9 minus x to the power of a half. And then what we need to do, when using the binomial expansion, we need to factorise out any number at the front so that this 9 becomes a 1. Now the good news about this is actually given to you in the formula book, the year 13 version of the binomial expansion. So I'm just going to pop this at the top, and then I'll show you and reveal what the formula book gives us. So straight from the formula book, we're told this: 1 plus x to the power n is this jazz here. So it looks much harder than what it is. Hopefully this solution will jog your memory. So what we need to do here is to rewrite f of x with the leading term being 1. So I'm going to just put this in big square brackets to the power of a half, factorise out the 9 from these curved brackets. That gives us 1 minus a ninth of an x, all to the power half. So take the power of half to both the 9 and the bracket. 9 to the power half is clearly going to be 3, and this one in the brackets becomes 1 minus a ninth of an x to the power of a half. So we're going to leave this 3 on its own on the outside, and then we're going to use this in yellow to help us perform the binomial expansion of 1 minus 1/9 x to a half. Multiplying 3 by 3 at the end will yield our final solution to this. So 3, then big brackets. All we're going to do now is apply this thing here to our 1 minus 1/9x. So our x is essentially minus 1/9x in our case. So 1 is the first one we have, plus the power times x, so plus a half multiplied by 1/9x minus. And we need to go up to the x cubed term. So the next thing is, we do the power times by the power minus 1. So a half times minus a half, all over 1 times 2. I think of this in terms of factorial, so that's 2 factorial, that just means 2 times 1, multiplied by our x thingy squared. Now our x is actually minus 1/9x, so we do that whole thing squared. And then the other one, going up to x cubed but no further, n times n minus 1, a half take away 1 is minus a half. The next one would be n minus 2. So minus half minus another 1 is minus 3 halves. All of that will be over next 1 times 2 times 3, which I'm going to call 3 factorial, multiplied by this thing here, cubed. So minus 1/9 of an x cubed. Now obviously it would go on and on, but we're just truncating it to the x cubed term. So we can forget the higher powers because they will converge to 0 as long as the modulus of this thing here is less than 1. So I'll leave it on the outside for now as we simplify. 1 is obviously 1. Half times minus a ninth is minus 1/18 of an x. This here, I think I might need the calculator for. So what we can do here on the calculator is just plug this in. So on the top, I've got a half. I'm just going to call this 0.5 out of laziness, times minus a half, minus 0.5, over 2 factorial. So 2 shift the x minus 1 button gives you factorial, like so. Get this on the screen for you. Then this is all going to be multiplied by minus 1/9 squared to get the coefficient of x squared. Now I know that minus 1/9 times minus 1/9 is 1/81. Just type it on your calculator as minus 1/9 all squared if you want to. That gives us minus 1 over 648. However, what's going to happen here is that will stay as a minus, because here, when I square something negative, it comes out as a positive, but this minus in the minus half will remain. So this minus sign is correct. That's minus 1 over 648 x squared. Similar process of this one. So over here, what we're going to have is half times minus 1.5. So I'm just going to edit this times minus 1.5. Next, that's over 3 factorial. And then that's going to be multiplied by minus 1 over 9 cubed. So I'll just show how to do this on a calculator if you want to. So that's going to be, well, I said I'll show you. It'd help if I actually do it myself. I can. I'm just having a bit of a nightmare. So minus 1 over 9, close brackets, to the power 3. And that gives us a coefficient of x cubed of minus 1 over 11,664, was it? Yes, it was. All to the power x cubed. Fine, now we can multiply all this by the 3. So that gives us, if you want to double check it, you can. 3 minus 1/6 of an x. This one, when I multiply it by 3, will give us 1 over 216 x squared. And this beast here, multiply that by 3, gives us 1 over 3,888 lots of x cubed. Binomial expansion questions can be quite long-winded, but the good news is they can also be lots of marks, because the examiner knows that they're not exactly a 2-minute question each. That's the warm-ups done. Let's now have a look at the main body of this lesson, differentiating not just trig functions, but also differentiating inverse trig functions. First of all, tan𝑥, sec𝑥, cot𝑥, and cosec𝑥. These are going to be given to you in the formula books, but I always want to try and prove to you why the case is as it is. So what we're going to do here is prove, using the quotient rule, the derivatives of these trig functions. So find f dash x rather, for the following functions in terms of x. Here we are. So I'm going to write up, starting, what the quotient rule is. So in shorthand notation, what I tend to say is that f dash of x is VUV over v squared, and the last things here are dashed. And that's where f of x is a function u over v. So that's what we're going to be applying here. We're going to be applying this thing to all these a, b, c, and d. So f of x equals tan𝑥. So in other words, the first one, f of x, how tan is defined, it's sine over cos. So rewrite it in terms of its components, sine over cos. Therefore, using this here, f dash of x is going to be the derivative of, so it's going to be v, the bottom, which is cos𝑥, multiplied by the derivative of the numerator. Sine differentiates to cos, so we're going to have cos multiplied by cos, then minus u, the function u is the numerator, that's sine x, multiplied by the derivative of the denominator. If v is cos𝑥, v dashed goes to minus sine x. And all of that is to be divided by the denominator squared. The denominator of tan is cos, so that's going to be divided by cos𝑥 squared, or cos squared x if you'd like. So the top, cos𝑥 times cos𝑥 is cos squared x. Minus sine times minus sine is going to be positive sine squared x, all divided by cos squared. Now, the top should have you thinking of a very basic year 12 trig identity. Sine squared plus cos squared always equals 1, as does cos squared plus sine squared, of course. So this is the same as 1 over cos squared x, and 1 over cos, if you remember, that's defined as sec, so 1 over cos squared is sec squared x. So in other words, the derivative of tan𝑥 is sec squared x, or sec𝑥 squared. What if we wanted to differentiate sec𝑥 itself? Let's think about what sec𝑥 is in terms of sine, cos, and tan. So sec of x is 1 over cos𝑥. Again, we can use the quotient rule for this one as well. So this time, our u is 1, v is cos. So using that, we're going to have the f dashed of x is v, the denominator, which is cos𝑥, multiplied by the derivative of the top. If I differentiate 1, I get 0 minus u, the top function, which is the 1, multiplied by the derivative of the bottom. So u is 1, cos differentiates to minus sine. And all of that's going to be divided by v squared, which in our case is cos𝑥 all squared. So cos squared x. Minus 1 multiplied by minus sine is going to give us positive sine of x all over cos squared of x. Now what I want to do here, I'm going to split the cos squared of x into a cos𝑥 and another cos𝑥. Because if we do that, we can rewrite this derivative in terms of two other trig functions. Sine over cos is going to be tan. 1 over cos is, of course, sec. So I'm going to write this with sec first, because this is how the Flynn book gives it. 1 over cos is sec𝑥, and sine over cos is tan𝑥. Therefore, the derivative of sec𝑥 goes to sec𝑥 tan𝑥. So it differentiates to itself with tan𝑥 stuck at the end. Part C, differentiate cot. What does cot mean? Cot is 1 over tan, so reciprocal of tan is cos over sine. That's cos𝑥 over sin𝑥. So f dashed of x is function v for denominator, which is sin𝑥, multiplied by the derivative of the top. Cos differentiates to minus sine, minus u, which is cos𝑥, multiplied by the derivative of the denominator. Sin𝑥 differentiates to cos𝑥, so it's minus cos𝑥 times another cos of x, all over v squared. So that's over sine squared x. So next up, simplify the numerator. So the numerator, sine multiplied by minus sine is obviously minus sine squared x. Minus cos times positive cos is minus cos squared of x, all divided by sine squared x. And again, the denominator we can keep as sine squared x, but the numerator should get us thinking. I can factorize out a minus here, so it's going to be minus sine squared plus cos squared of x, all over sine squared x. And of course, sine squared plus cos squared equals 1. So we're going to have minus 1 all over sine squared of x. 1 over sine is, of course, cosec. So 1 over sine squared is going to be cosec squared. Don't forget the minus. So it's actually going to be minus cosec x squared. In other words, cot of x differentiates to minus cosec x squared. The last one to prove and show is the derivative of cosec of x. So again, rewriting it in terms of what cosec is in terms of sin, cos, and tan. Whoops, get back into a black colour. We have f of x is 1 over sine of x. And once again, for the fourth time in this little exercise, we're going to use the quotient rule. So f dashed of x is going to be the denominator, sine x, times u dashed. 1 differentiates to 0, minus u, which is the numerator, which is 1, multiplied by the derivative of the denominator, which is cos𝑥, And that's all going to be divided by the denominator squared, which is sine squared. So this one is just going to be minus cosx over sine squared. And again, in a similar way, what I want to do is section this out into two things. I'm going to section this out into a minus cosx over sine x multiplied by 1 over another sine x. Cosx over sine x is the reciprocal of tan x. In other words, cosx over sine x, you should know, is cotx. So this gives us minus cotx, and 1 over sine is, of course, cosec. So minus cotx cosec x. Or if you write it a different way around, cosec x cotx. So those are the 4 key derivatives which we're going to be using in this chapter. So that's how you prove them. So let's move on. From these results, a simple application of a chain rule allows us to generalize even further. So if it wasn't just differentiating a simple tan of x, a simple sec of x cotx, if we had a constant k at the front, all that happens is the k would come to the front of what we've just proven on the previous bit a few moments ago. If you're not sure of how to prove this yourself, you could use the chain rule and just differentiate tan u, where u is kx. So that could be a self-guided extension if you want to convince yourself these hold. The good news is, which I mentioned to you before, these are fortunately provided in the exam formula book. So there's still lots to learn and still lots to know, but the examiners at Edexcel do have a bit of a heart. They do know that your memory is finite. You are thankfully given these. If you can remember them, that's even better. If not, though, do please remember they are given to you. So it's not the end of the world if you do forget them, but please do try to remember these key results. Makes your life much easier. So let's now apply this with some worked examples. So, first of all, worked example 1. Differentiate y equals x squared tan 3x. So what we can see here is it's clearly going to be a product. It's a product of x squared and tan 3x. Firstly, let's just remind us of those previous results on the other slide. What we had from before is this, which we may as well use. So we know we can differentiate tan 3x by using this top line. So tan 3x means our k is 3. So just highlighting that. This is the product, as I say, of an x squared times tan 3x. So just remembering, if we differentiate a product, uv dashed, it's uv plus uv, where we differentiate one, leave the other alone, then leave the one we differentiated alone, differentiate the other. So it all depends what we want to call our u and v. What I'd suggest is u can be the first product, which is the x squared, and v can be tan 3x. So here, if I differentiate u, differentiate x squared, that's going to give me 2x. If I then multiply that by v, which is just tan 3x, then plus the function u, which is, of course, x squared, multiplied by the derivative of tan 3x. This is where this form is going to help us. So differentiating tan of 3x will be 3 sec squared 3x. Can't talk tonight, that's very sad. So 3 sec squared 3x. We can now ever so slightly neaten this up. So what I'm going to suggest we do here is just expand it out, to be fair. So what we're going to have is 2x tan 3x plus 3x squared sec squared 3x. And that's absolutely fine. If the examiner wants you to factorise, they'd normally say, you could factorise out here an x, of course, but if in doubt, this is absolutely fine. Unless the examiner asks you to factorise, don't feel like you need to do an extra step too much. this is fine. The derivative of x squared tan 3x is therefore 2x tan 3x plus 3x squared sec squared 3x by using the product rule. For work of example 2, I thought we could try differentiating y equals tan squared of 5x. Before we get into actually applying it, I think it's only fair to remind us of the 4 key results we've just seen and shown in the formula book, which are these. So these are going to help us here, especially differentiating tan. But here, we're differentiating y being a function of tan squared. So what we can do here is actually apply the chain rule. So if I say let y equal u squared, where u is simply tan of 5x, then we can apply the chain rule to this. So if u is tan 5x, we can use this result here with our k value being 5 to work out what du by dx is. So just looking at the top line here, with our k being obviously 5, then differentiating tan of 5x will give us 5 sec squared 5x. So therefore, du by dx, like I just said, is going to be 5 sec squared 5x. So therefore, dy by dx, using the chain rule, is dy by du multiplied by du by dx. So if y is u squared, if I differentiate y with respect to u, bring the power to the front like we knew from year 12, dy by du is simply 2u, and du by dx, like we've seen, is 5 sec squared 5x by using these results in the formula book. So let's simplify. 2 times 5 is 10. If we plug u back in terms of the variable the question was given in, which was in terms of x, our u was tan 5x, wasn't it? So I'm going to say that's 10 tan 5x sec squared 5x. And that's the derivative. So that's all we need to do. 10 tan 5x sec squared 5x. Let's now have a look at the final one of this section, worked example 3. Here we need to differentiate a quotient. It's cosec 2x all over x squared. So again, just remind us of the key results from before, which are these ones. We can now apply both the quotient rule and these results to compute the derivative of this. So our u is cosec 2x, and the denominator is x squared. So v dashed is going to be 2x, and if I differentiate cosec 2x, we can use this result here with our k being equal to 2. So differentiate cosec 2x, that's going to be minus 2 cosec 2x cot 2x. So just using that result here, which we saw. Then remembering the product rule, the quotient rule, u v dashed is vuv / all over v squared. So all we need to do here is just fill in what our v, u dashed, v, and v dashed are. So if I let u, it's cosec 2x. If I say u dashed is this, which of course it is, v is x squared, and v dashed, therefore, is obviously 2x like we said before. So v dashed is that. So just plugging in these values, v times u dashed, that just means x squared, multiplied by u dashed, which is minus 2 cosec 2x, cot 2x. And then we minus from that u, which is cosec 2x, multiplied by v dashed. V dashed is just simply the 2x. All over v squared. So v, of course, is x squared. X squared squared again gives us x to the power 4. So that's just going to be x to the power 4. So we've got it here. All we need to do now really is just try and neaten it up if we can. So what I'm going to suggest we do is just to expand this out after we can simplify by cancelling an x on numerator and denominator. X squared divided by one of these x's will give us just 1x. We can change that to x cubed. And of course, if I divide this one by x and x down here, that x will cancel. So cancelling an x on the top and an x on the bottom, what we can do next is simplify this and expand out as well. So the top, this now is just a single x. That gives us minus 2 times x cosec 2x cot 2x minus 2 times cosec 2x all over now x cubed. That's normally fine, but what we could do is just go a slight step further. So if we just simplify now and factorise slightly further, I'm hoping you can see here that there is a common factor of a 2 and an x. There's a common factor of a 2 and an x and cosec 2 of x. So in both these cosec terms are minus, so we can actually factorise out on the top minus 2x cosec 2x. So minus 2x cosec 2x. Over here we have to write in cot 2x. This is minus. We want to keep it as a minus. Minus and minus will make a plus. We don't want that, so just leave it as a positive for the next term. We've got minus 2x cosec 2x. This is the same thing again, so we just need to multiply it by 1 to get itself back, all over x cubed. And then we're done. It's factorised into a slightly nicer form. We've cancelled out the x on top and bottom. That's the simplest way of writing the derivative. So slightly harder than example 1 and 2, but sometimes it's worth showing you some harder examples, of course. Let's now move on to talking about differentiating inverse trig functions. Like I said, I'll stress this again, this isn't now in the A-level spec, but I think it's a nice little application of what we've seen before in this chapter. So let's have a look at how we'd prove the derivatives of arctan𝑥, arccos𝑥, and arcsin𝑥. That's tan minus 1, cos minus 1, and sine minus 1 in old money. So here we're going to use this application that dy by dx is reciprocal of dx by dy. And if you remember some earlier identities, we can work these out without actually too much trouble. So first of all, let's have a look at differentiating the function where the function is y equals arcsin𝑥. And I'm going to put the graphs of the inverse trig functions on the right hand side of our screen just to remind you in removing some ambiguity. What ambiguity do you say? All will be revealed in just one moment. Just bear with me and I'll explain what I mean. So, like I say, let's differentiate arcsin𝑥. Before we do so, I'm just going to remind you of a graph of arcsin𝑥. Why am I doing this? It'll make sense in just a moment. But what we're going to do now is we can set y to be arcsin𝑥. So allow y to be arcsin𝑥. Then if we take the sine function of both sides, we'd see that sine y must be the same as sine of arcsin𝑥. The quick trick to this is sine of arcsine, this is a function of its own inverse. So f minus 1, sine and arcsine cancel each other out in a simplistic way of thinking about it. This right will just give us x. On the right hand side we'll just have x, so sine y equals x. So in other words, therefore, x equals sine y. So that's how x is sine y. We're just taking sine of both sides to find this out. So we're now going to differentiate sine y with respect to y. So rather than doing dy by dx, let's differentiate sine y with respect to y. So sine of x would go to cos x if we differentiate with respect to x. If we differentiate sine y with respect to y, in the same way, we get cos y. So now what we do is reciprocate this. So if dx over dy is cos y, then dy by dx will be the reciprocal of cos y, which of course is 1 over cos y. Doesn't look anything like this yet. However, we just need to remember a very key identity. Remember, sine squared of whatever, in this case our variable's y, plus cos squared of y, the identity is that always equals 1. So therefore, cos y is always going to be the square root, remember, plus or minus 1 minus sine squared y. So what we're going to do here is we're going to switch cos y in place of what it is in terms of sine squared. So cos y is actually this. So I'm going to replace cos y with it written in this form. So dy by dx is 1 over cos y, where cos y is plus or minus the square root of 1 minus sine squared y. So that's 1 over plus or minus the square root of 1 minus, well, what was sine y defined as? Well, sine y is x, therefore sine squared y just means x squared. So this is ambiguous, like I said here, ambiguity. Is it plus or minus the root of 1 minus x squared? Well, remember, when we take the derivative, we're essentially finding the gradient function. Look at the gradient here. By inspection, you can hopefully see the gradient of this graph. If you take the tangent at any point, the tangent's always going to be sloping upwards. So for example, taking the tangent here, that's going up. The tangent here is going up. Between the limits of where arcsine is defined, it's always going to have a positive gradient. Therefore, we can remove the minus. So just by making a note here, the gradient of arcsin𝑥 is clearly positive. We can remove that minus. So therefore, a bit by inspection of the graph, it must be that dy by dx is 1 over the positive root of 1 minus x squared. So what we were differentiating? We were differentiating, of course, y, where y is arcsin𝑥. So in other words, for derivative of arcsin𝑥, d by dx of arcsine of x must be 1 over the positive root of 1 minus x squared, for the reason where you can clearly see the gradient of this graph is positive throughout. Question 2, very similar to question 1 in fact. We're going to prove now that the derivative of arccos𝑥 is minus 1 over the square root of 1 minus x squared. So again, what we're going to say, similar to question 1, let's allow y to be arccos𝑥. So in the same trick as we did before, we can take cosine of both sides. So in other words, that gives us x is cosine y. Now we can differentiate x with respect to y. Dx by dy, differentiating cos y with respect to y. Cos differentiates to minus sine. So we get minus sine y there. So that tells us, by reciprocating dx over dy to give us dy over dx, we're going to have minus 1 over sine y. Again, if we just remember that sine squared plus cos squared is 1, we can again, like we did in the other worked example, we can replace sine y in place of cos squared. So in other words, if we simply subtract cos squared y from both sides, then square root, sine y is going to be plus or minus root 1 minus cos squared y. So I'm going to just replace sine y with this expression here, because then I can get it back in terms of x, which is what we need. So this is going to give us minus 1 all over plus or minus the square root of 1 minus cos squared y, which of course is minus 1 over plus or minus the square root of 1 minus, well, x is cos y, so cos squared y is therefore x squared. But how do we know if it's plus or minus? This is where again we're going to use the graph to help us decide. So recalling the graph of arccos𝑥, we have this here. And like before, question 1, where the graph of arcsine was clearly positive throughout, this clearly is negative throughout. So what we're needing here, quite clearly, is we want the gradient to come out to be negative. For that reason, we've got minus on top. We want it to be positive on the bottom, otherwise a minus and a minus would make it a plus. So therefore what we need is just the positive root 1 minus x squared on the denominator. So we can therefore conclude by saying, by inspection of the graph, or using previous results, quite clearly d by dx, the derivative, in other words, of arccos𝑥 is minus 1 all over the root of 1 minus x squared. Question 3, we're going to have a look at differentiating arctan𝑥 now. So let's prove the derivative of arctan𝑥 is 1 over x squared. So what we're going to do here, you can probably guess actually, we're going to let y equal arctan𝑥. If we apply tan to both sides, tan y is tan of arctan of x, which just gives us x. So in other words, x must be tan y. Differentiating tan y with respect to y, in other words dx by dy, we need to remember what tan differentiates to. This is one of the results we used and proven. Tan differentiates to sec squared from earlier in the video. So therefore dy by dx is the reciprocal of that, which is going to be 1 over sec squared y. Now this isn't immediately obvious what to do here, but what we do need to do, I can tell you, we need to remember an identity for sec squared and tan squared. So how does tan squared relate to sec squared? What we need to know is that 1 plus tan squared is the identity for sec squared. So just remembering this identity from earlier in the chapter, and my stupid way of remembering it, which I may have mentioned before, if we take one person and give them a tan, that person may find themselves being sec c in their own mind. Sec squared, sec c, it's a bit stupid, maybe slightly inappropriate. I don't particularly care as long as it helps you to remember. If you want to do it just by pure memory, 1 plus tan squared is sec squared y, if you're more sensible than me, which isn't hard to accomplish. So I'm just going to switch the sec squared y with 1 plus tan squared y using this identity, which you do need to know. But of course, what did we define tan y as? Well, defined y as arctan𝑥, so x is tan y, therefore tan y all squared, tan squared y, is x squared. So that's our result given, 1 over 1 plus x squared. That is the derivative of arctan𝑥. I'll show you the graph. This isn't actually ambiguous, this one. 1 is positive, 1 is positive, x squared has to be non-negative. So this comes out to be positive. So if we remember the graph of arctan, you should find that it's entirely positive. Let's just double check and confirm that to ourselves. Here it is. You can see clearly it is positive throughout. So that confirms this result here. So it makes sense in both levels. The derivative of arctan𝑥 is indeed 1 over 1 plus x squared. Let's now take it up a notch and try and differentiate something a bit meatier. So this, if you like, is quite the extension question if you want to have a go at it. Question 4, let's differentiate y equals arctan x squared over 1 plus x. So this is a mixture. This, essentially, we're going to use the result from before and then the chain rule embedded in. So what we're going to do here, we're going to let y equals arctan of u, where u is x squared over 1 plus x. So I'm just setting our u function to be x squared over 1 plus x. What we can do here is work out u dashed, in other words, differentiate this, which in itself is a quotient, so we can use a quotient rule. So if I just put this in the corner, and let's see if we can remember how to differentiate a quotient. So we've done it before in this video, differentiating a quotient, so same idea entirely. We essentially, to do u dashed, what we're going to do is take the denominator, which is 1 plus x, differentiate the top, which is 2x, then minus, this square isn't big enough, let's make it slightly wider, then we're going to minus off from that the top, the numerator, which is x squared, multiplied by the derivative of the bottom. So derivative of 1 plus x, 1 differentiates to nothing, x goes to 1, that's all over v squared, the bottom of it squared, in other words, so 1 plus x squared, which can be neatened up. So at the top, we're going to have 1 times 2x, which is 2x. X times 2x is 2x squared. Then we minus off one of those x squareds, so it's going to be left on the top with 2x plus 1x squared, all over 1 add x, all squared. So we know u, therefore we know what u dashed is as well. So u dashed is going to be 2x plus x squared all over 1 plus x all squared. So we can now use the chain rule. Now we know what du by dx is, which is 2x plus x squared, of course, like I just said, all over 1 plus x squared. So dy by dx is going to be dy by du times du by dx. So before, what we need to remember is what arctan differentiated to from worked example 3. Well, arctan differentiates to 1 over 1 plus x squared. So if I differentiate arctan u, that's going to be 1 over 1 plus u squared, because I have an arctan𝑥, we're talking arctan u. So it's going to be 1 plus u squared. And du by dx, we've just worked out here, I called it u dashed, it's this 2x plus x squared all over 1 plus x all squared. So we can multiply the top together, so 1 times 2x plus x squared is just going to be obviously 2x plus x squared. Replacing u in terms of what u is in terms of x, remember I said y is arctan u, so if I were to replace u with what u is, which is this thing here, then we're going to have on the bottom 1 plus this thing here all squared, so x squared over 1 plus x, which of course is, this is our u, that's all squared, times this other denominator, which is going to be multiplied, therefore, all of that times by 1 plus x all squared. Make this fraction line slightly bigger because it doesn't quite encompass all of this horrible denominator. There we go. So now we can just finally, in the last step, neaten up this denominator. So the top, if you want to, you can factorise out the x. In fact, why not do that? So I've got x brackets 2 plus x. Then here, 1 multiplied by 1 plus x squared is obviously just 1 plus x squared, all squared rather, and then x squared squared is x to the 4, and then the denominator 1 plus x squared, when I multiply by this, that will cancel. So I'm just going to be left with x squared squared, which is x to the power 4. So quite a beastly derivative, but it's worth showing you these now so you're not freaked out in the exam when you do get some hard ones. The derivative, therefore, of arctan of x squared over 1 plus x is x, brackets 2 plus x, all over 1 plus x squared plus x to the power 4. Phew. Now I'm hoping that fairly meaty chapter and lots of worked examples will be a good preparation for this. So, if you open your books, turn to page 249, attempt all of exercise 9F for more practice the better, and let me know if you do get stuck or do struggle. The more you do, the better you'll become. So as always, do let me know if you're struggling in the comments or on an email or in class. Do keep in touch and tuned in for the next video. Take care of yourselves, and I hope to see you all very soon indeed. So for Mr. Bailey, goodbye, and for me it's good night too. So farewell, see you next time.